In the previous session, and the two sessions actually, we look at how the ball plots of an open loop transfer function can be used to determine whether or not a closed loop system is stable or not. And there are some parameters we can identify: the crossover frequency, the frequency where the phase plot crosses 180 degrees or minus 100 degrees, that's my omega 2. And we'll also be able to identify the phase margin and gain margins. If we know K and we know G, and therefore we have the ball plots of G times K. Now, of course, for someone to design a controller in order to meet certain requirements, you will not have the KS. Okay? In the examples I gave, we were assuming certain values for KS. Sometimes we have to guess, but most of the time we can't, because we have to follow strict design rules so that we don't waste our time. So the trick is how to actually find the KS that will meet the requirements for any given GS. GS is your plant. Okay? So we need to actually know how to design controllers. And one of the techniques we already covered is Rudnick's diagram, which allows you to tune a particular control gain. But that's only one gain at a time. Now, in this session, I'm going to introduce a design method for a particular type of controller. It's called a phase need compensator. Okay, how to actually to meet the design requirements based on what a system, open loop system we have. Okay, the phase need compensator has a transfer function as shown in equation number 1 here. Okay, so Ks equals to some small k, which is the control gain, which is also the dc gain of that transfer function. Okay, the transfer function Ks equals to k times, in the numerator is alpha times tau times s plus 1. In the denominator, it's tau times s plus 1. We have 3 parameters for the design. One is k, how much we need that for that. One is tau, that's another value. One is alpha. Now, of course, we have 3 values to tune, or 3 parameters to tune. Therefore, it gives us a lot of flexibility in the control design. This transfer function will give you a positive phase angle when alpha is greater than 1. Okay, we're not deciding what exactly the alpha value should be, but we know the range needs to be greater than 1 to give us a positive phase angle. That's why it's called phase need, because it gives us a more positive phase angle. Okay. Now, to work out some of these parameters, I have other 2 equations that can be used. One is to work out the alpha value from how much phase angle we want. Okay, so say if we want a particular value of phi, then I can use this formula to work out the alpha value. So I know alpha will determine how much maximum positive phase angle I can get out of this compensator. Okay, so alpha value is related to the phase angle. But also, I can use tau to determine where I want that positive phase, or at what frequency I want that positive phase angle to be. Now, to calculate that, you basically use the alpha you worked out from equation 2, and then put the frequency in there. This omega m is where I want that phase angle to be. Okay, so equation 1 defines the transfer function of the phase need compensator. Equation 2 is the one you use to calculate alpha value for the controller from the required phase angle. Okay, tau, equation 3 is what you use to calculate the tau value so that the phase angle you wanted will be at the exact frequency you wanted as well. So there are two things we need to make sure that's right. I'll talk about how to design the control K, the small k, later in an example. Okay, so for example, if I given this requirement, say I want a maximum phase need angle of 45 degrees, and I want that happen at 10 radians per second. Now, if you are given conditions like that, then the calculations are easy. You just substitute 45s into here. You substitute this frequency into equation number 3. Okay, so here we go. 45 degrees is the phase angle I want, so I'm going to put 45 here. I'm going to put 45 in the denominator. 1 plus sine 45 over 1 minus sine 45. You use your calculators, and that will give you a value of 5.83 approximately. Then I know omega is 10. I want that happen at 10 radians per second, so I'm going to use the third equation, equation 3. Tau equals to 1 over square root alpha. Alpha, I just worked it out. So I'm going to put alpha 5.83 in there. Omega is 10, so I'm going to put 10 there. That will give me 0.04. Sorry, 0.0414. Okay. Put alpha and tau value back into equation 1, and I'm going to plot the both plots. Okay. At the moment, I'm assuming the small k equals to 1. So you can see there, the second plot here, which is the phase angle of the Ks, gives me a 45 degrees. This is 40, this is 50, this is halfway. 45 degrees at 10 radians per second. Now this 45 degrees doesn't happen at other places. You can see if the frequency is lower, at lower frequency, the phase angle goes down. At high frequency, the phase angle also goes down. So only the maximum phase angle you get out of that transfer function is only at your design frequency. Okay, so it's that phase angle we want for our design in the phase need compensators. Okay, now of course, if you notice that the magnitude also changes with frequency. So it's not a constant, it changes with frequency. And of course, because when you consider k times g, you add the magnitude to magnitude. Okay, so you add magnitude of this ks to the magnitude of gs. This will change the overall magnitude. Therefore, your crossover frequency will change. Okay, and you add the phase angle to the phase angle of this ks to the phase angle of gs. That will change omega 2. It will change the phase margin and so on. But for design, for particular design, we normally ask, say, we want the overall phase margin and the overall gain margin, the overall crossover frequency. So we need to consider both G and K at the same time. Typically, you will be given the GS or the both plots of GS. You want to design the KS, or you want to work out all the parameters in KS so that they meet your requirements. Okay, and that's all a bit vague. So I'm going to use an example here. Okay, now example is the one that I use quite often, which is a satellite tracking radar. The transfer function of GS is given in equation 1. That's 1 over s times 10s plus 1. I have a requirement for the system to follow a particular ramp input. And previously, I worked out the requirement for the minimum damping, the K control gain, and natural frequency for the closed loop. Okay, I'm going to actually I have actually interpret this requirements on the left onto the parameters we can use. What I want, in order to meet the requirements in this box, I will need the crossover frequency of 0.8 radians per second. I want a phase margin of 60 degrees. Now, crossover frequency and phase margin, in this case, in this particular application, applies both to G and K. So it's, if once we design the KS, if we add KS and GS together, the crossover frequency should be at 0.8 radians. At this frequency, I should have a phase margin of 60 degrees. So that's my design aim. Okay, so bear that in mind. Equation 3 defines the required crossover frequency. Equation 4 defines the required phase margin for the closed loop. GS in equation 1 is the transfer function of the plant. Okay, it does not include the KS. Now, if I plot the bow plots of the plant GS, this is what I get here. So I get the bow plot diagram of the plant GS. Again, I'm emphasizing it does not include the KS. Now, if you look at this plot, I can actually check 0 dB. I can actually go there, 0 dB is there. Now, crossover frequency is 1, 2, 3 at 3 radians per second. Sorry, 0.1, 0.2, 0.3. This is not what we are asking. Okay? We are asking for 0.8. So the crossover frequency, after you add KS to it, should be at 0.8. Okay, a mistake people often make is actually they go there, they go to the current crossover frequency from GS alone, and then try to do your design, but that's not what we want. We want overall crossover frequency when we have KS as well to be at 0.8. So the first step of a design is actually work out how much we already have from GS alone without KS. So I go to, instead of the current crossover frequency, I go to the frequency where we want the crossover frequency to be, not where it is now. This is what we want. What we want is 0.8, so I'm going to go to 0.8. 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8. Okay, so that's where 0.8 is. And ideally, well, it helps if you draw a vertical line there. And then I can read two values out of the bow plots of a GS. So for the magnitude, now this is just MATLAB doing a live stream for me. It reads the value for me. Okay. For the magnitude, I have a minus 16.2 dB. For the phase angle, I have 173 degrees. That's what I already have. Without controller, this will give you a phase margin of 7 degrees, right? Because it is 7 degrees away from minus 180. But we also need to change the gain as well, because I want the crossover frequency to be at this one. Therefore, it needs to go up. This graph needs to go up. Okay, you don't have to shift the whole thing up. Hopefully, when we finish design our KS, I put them together, they will meet the requirements. Okay, so first step is read the value out of GS, the plant. Okay, that's what I've just done there. So I go to the design frequency, not the current crossover frequency, okay? Because we have a new requirement there. We want crossover frequency at 0.8. So you go to 0.8, that's read the values out of magnitude, read values out of phase angle, or estimate if you have a plot. Okay, because I have the values there, exactly the values there, because I have access to a computer. I know how to use MATLAB. So read values out at 0.8. I have minus 16.2 dB. I have 170 degrees. That's step number 1. Step number 2 is to work out how much more you want from the KS, the controller. That is the difference between what's required and what you already have from the plant. Okay? So the difference here is what's required. I want crossover frequency at 0.8 and I want phase margin of 60 degrees. So therefore, from the controller, I want something more. The plant give you a phase angle of 173. Therefore, the difference between 173 and 180 is 7. So the plant will give you 7 degrees. So I need actually 7 degrees, but I want overall 60. So 60 minus 7, that should give me 53 degrees. Okay, not 57. So that's my first requirement for the controller. So I want a maximum phase angle I get out of the controller to be 53 degrees. But I also want a crossover frequency at 0.8. In the first step, what I found is actually magnitude of GS is minus 116.2. Therefore, I want the controller to give me a positive 16.2 dB. Positive 16.2 plus minus 16.2, that will give me a 0 dB. So add together, you get 0 dB. Okay? 0 dB, that's where the crossover frequency will help. So I want my magnitude from the KS to have a gain of 16.2 dB at the crossover frequency, that's omega C. Of course, I need to convert that into a log value. That 16.2 is the dB. dB equals 20 log 10 to the power n. So I need to work out actual gain rather than the gain magnitude in dB. Now, 16.2 is here, that's 8 dB, equals 20 log 10. Therefore, the actual gain, actual AC gain at this frequency should be 10 to the power of the dB value divided by 20. It's just a bit log for you. So if you get lost here, then you need to go away and revise your log a bit. Okay, so positive 16.2 equals 20 divided by 20, and then 10 power of that will give me 6.465 for the DC gain, or the magnitude of DC gain, AC gain. So magnitude of AC gain at this frequency. Okay, that's my equation number 10. Now I know my crossover frequency. I know how much phase angle I want out of the controller, and I know the AC magnitude of AC gain at that frequency from the controller as well. Then I can go on to my design. So step 1 is to establish how much we have already from the plant. Step 2 is to work out how much you need from KS, the controller. Step 3 is to work out the values of alpha and tau. Work out alpha value is easy because we want 53 degrees out of the controller. That's equation 7. Okay, so I'm going to substitute this by 53, substitute this by 53, and that will give me an alpha value of 8.93. We want that angle at 0.8 8 radians per second. That's frequency. So I'm going to use this frequency to work out the tau value. Okay, so tau equals to 1 over crossover frequency, square root alpha. Do the calculation here, I get 0.42. Substitute alpha and tau value back into my transfer function here. Alpha equals to 8.93, tau equals to 0.42. So this is alpha, this is tau, this is tau there. I'm leaving that small k there. And multiply 8.93 and 0.42 together, that will give me 3.75. Now that's end of my step 3. Now I work out alpha value and I work out the tau value. The next step is actually try to work out that k value. So that's my next step. To use the k value, we need the magnitude of the AC gain we wanted from the controller. That's what we work out in the step number 2. We wanted this value, 6.64. We need to use that. Okay. Now to find this is your controller you got from the step 3, and then we want to determine this. To determine this, the first thing you need to do is to replace this S and that S by J omega C. Omega C is my crossover frequency, or required crossover frequency. This is 0.8. So I'm going to replace this by J 0.8. I'm going to replace this S by J 0.8. Now if you look at this is a complex number. Okay. Complex number will have magnitude, will have phase angle. Okay, and it just happens, after I've done my calculation, the magnitude of this part is 3, the phase angle is 52. Or 53, as I said. Actually, it should be 53, because that's what we wanted from it, so we should get 53. You can double check, just to make sure my calculations are right. It will be probably 52 point something because I rounded up some numbers. Okay. Now to find this k, the only thing I don't need the angle here. The angle is what I designed for, so I'm not too worried about it. I don't need the angle here. Only thing I need is this magnitude. I want that k times 3 equals to m value I work out in step 2. Okay, in step 2, I work out this m value. 3 times k equal to m. M is 6.465. Therefore, k equals to 6.465 divided by 3, or 2.15. Substitute that 2.15 into equation number 15. I end up with my controller. That's all 3 parameters to determine. Okay? Just to recap what we've done. We have a set of requirements. We want, well, actually we have only 2 requirements. We want the crossover frequency to be at 0.8. We want to phase a margin of 60 degrees. So the first thing you do, step number 1, you go to the ball plot of GS, and you go to the design frequency, which is 0.8. You read the value out of magnitude plot, you read value out of phase angle. Okay? Or estimate it if you must. So that's your step number 1. You read these 2 values out. Step number 2, you need to work out what you need from the controller. This is our requirements. 0.8 is the angle, is the crossover frequency. Margin is 60 degrees. From this, and from what you read before, we can work out the difference between 180 and what you read from GS, which is 178. And then you do a 60 minus that. Okay, 60 degrees is what we want. 180 minus 173 is what we already get from GS. Okay? Therefore, what we need from the controller would be 53 degrees. For the magnitude, because we read from GS minus 16.2 dB at the design frequency, therefore we will need a positive 16.2 dB from the controller at this frequency. Okay? In order to have a 0 dB. 0 dB is where it costs you the frequency where 0 dB is where the cost of frequency is. Okay? So then from what you need 16.2 dB from the controller, but you need to work out the actual gain instead of the dB. Actual gain, use this formula. It's 10 to the power of dB value divided by 20. That will give 6.465. So that's your step 2. Step 3, you're going to use crossover frequency and required phase angle to work on alpha and tau value. Okay? We want 53. That will give us alpha value. We want 53 at 0.8 radians per second. This will give us the tau value. Then you substitute alpha and tau back into the transfer function of the controller, leaving that small k to decide in the final step. Okay, so in the final step, you replace S by J 0.8. 0.8 is my design frequency. Okay, so replace that S by J 0.8, replace that S by J omega 8. And this becomes a complex number. Work out the magnitude, work out the phase angle. The phase angle should conform to my requirement, okay? Because we want 53 degrees out of controller. And this is the controller, or the transfer function of the controller. Then you equate the magnitude you have here, 3 times k, equals to what you work out the gain you needed from the controller. That's what you work out in step number 2. And then, of course, from there, you can work out a k value. So stick k to the front. That will be a controller. Next thing, if you have access to the controller, I can check. I check my design. This is the transfer function of the plant, the GS. This is what I just designed. So I multiply the two together, G times K, and I go to MATLAB. Plot. Ask MATLAB to do the bow plots for me for the G times K. Okay, not just G alone, or the K alone. And I get this. If you go across there, 0 dB, I get 0.8. At 0.8, I get 100 minus 120 degrees. Minus 120 degrees is 60 degrees away from minus 180. Therefore, I have a phase margin of 60. That's exactly what I ask you to design. Okay, crossover frequency at 0.8, a phase margin of 60 degrees. And I can do more checks. I can check the performance as well using MATLAB. So I've gone to there, I actually built a model in there, and I give the input a step, and they give me that kind of response. Okay, now of course, checking is not part of requirement if we're talking about, if you're thinking about exams, okay, because I won't give you a computer. All I won't ask you to use a computer to check the performances. Now it's your turn, okay? This time, I'm giving you the bow plots of a GS, which is different from what my example is. GS is given here. What I like you to do is to design and phase need compensator to give me a crossover frequency of 100 radians per second and phase margin of 45 degrees. Okay, so the steps go through the 4 steps exactly the same way as I did. You should get your controller. Thank you.